Hello everyone, welcome to my presentation. I'm Yutong from University of Western Brittany, and my research is attached to the activities of Laboratory La team, which belongs to the INSERM institution of France. Today I have great pleasure in introducing my paper, two-stage multi-scale mass segmentation from full mammograms. According to the statistics in 2020, breast cancer is ranked first as the leading cause of global cancer incidence among women, representing about 25% of all cancers in women. Over the past few years, the massive screening has allowed earlier diagnosis and better cancer management, thereby greatly improving survival rates. However, due to the non-systematic double rating, the proportion of women recalled for further examination after screening remains still high, resulting in a high recall problem. About 100 over 1,000 women screened are recalled for additional tests and unnecessary treatments, while only about 5 are truly affected. So in this context, computer-aided diagnosis system for mammography has been introduced to provide an objective view to radiologists. But conventional GAD systems are usually inefficient and not automatic enough to significantly improve the diagnosis performance. It still needs to further improvement to assist the clinicians in interpretation. In this work, we study X-ray mammograms. X-ray mammograms is the main imaging modality for early diagnosis of breast cancer. Among various types of breast abnormalities, breast masses are the most important clinical symptoms of breast cancer. However, low contrast and high variance in mass characteristics such as size, shape, texture, and contour make it difficult to locate and segment masses from the native full mammograms. To conduct X-ray mammogram study, we use 2 public datasets in our work. One is the INbreast. It is quite small dataset with only 107 mass cases. The advantage of INbreast is that it provides very precise annotations of mass. Another dataset is the DDSM-CBIS. It's relatively larger, but it provides only coarse delineation of mass. Mammogram analysis mainly includes the localization of the suspicious areas and then to segment or classify the lesion. Due to the unpredictable variations in mass characteristics, a good delineation of mass is essential for further classification of the mass into benign or malignant. However, as you can see from the left, the difference between image size and mass size can be enormous. Most existing methods focus on segmentation from downsampled low-resolution mammograms or from manually extracted suspicious areas, which largely simplify the segmentation process, but at the expense of the robustness and the applicability in clinical practice. So in this work, we aim to build a fully efficient and automated mammogram analysis system, which takes native full mammograms as the input and both accurate mass localization and segmentation as the output. The ultimate goal is to reduce the interpretation workload of radiologists. The challenges are that localizing mass areas from mammograms and finding precise boundaries for each mass are naturally 2 tasks with contradictory focuses. Mass localization focuses more on the context-level semantic information, while mass segmentation focuses more on the resolution-level details. Addressing both challenges using a single deep network is not an optimal choice due to the limitation of computational ability and the resection fields that increase with network depth. And another challenge is the strong imbalance between mass regions and the background areas. To tackle the aforementioned challenges, we propose a two-stage multi-scale pipeline, which performs automatic and highly precise mass segmentation from native high-resolution X-ray mammograms. Our framework consists of two steps. So for a given mammogram with native resolution, we first perform image-based mass localization using a novel multi-scale fusion strategy for automatic mass selection. Second, we employ a convolutional encoder-decoder architecture with nested and dense skip connections for precise region-based mass segmentation. Finally, the visualization of the segmentation results can be easily realized from the original mammogram. Specifically, for mass localization, we can train the detection model at multiple scales, such that the localization procedure can also be extended by fusing predictions performed at multiple scales. As shown in this figure, feature maps from different scales are used to deal with huge mass size and aspect ratio variance. In other words, larger feature maps are assigned to detect smaller masses and vice versa. In this work, we employ ULOV3 for mass localization thanks to its good trade-off between accuracy and efficiency. Other detectors such as SSD, faster RCN, RetinaNet, and so on can also be applied as alternative detection schemes. In this step, we aim at identifying masses of any size, position, or shape from the whole image, regardless of the resolution details. Particularly, I will explain how the multi-scale fusion strategy works. First, detections are carried out at different mammogram scales. For each bounding box, we create a confident mask MI where the value of the box area is the corresponding confidence score. Then, a single confidence mask MS will be created by fusing all confidence masks obtained at each prediction scale. The fusion operation is firstly to sum, then to normalize. After MS is created, we consider an empirical threshold lambda to implement majority voting to the fusion mask MS, which in other words, to keep areas where MS greater or equal to lambda. Afterwards, all connected regions of MS are assigned the same label. Finally, we measure the properties of labeled MS and find the bounding boxes that describes the fusion mask most properly. The principle behind the multi-scale fusion strategy is to focus on redundant information that appears at multiple scales. Statistically, the multi-scale fusion allows to identify the most frequently detected regions in multiple prediction maps in order to eliminate false positive predictions. On the other hand, regions detected in few prediction maps or areas with low confidence scores are unlikely to be selected. Final detections are resized to 256 by 256 patches and fed into the segmentation stage. We implement a deep convolutional encoder-decoder architecture with nested and dense skip connections named UNet++. The architecture is derived from the standard UNet. We employ in practice the VGG19 as backbone for the encoder. The decoder is symmetrically designed, and the proposed mass segmentation architecture is referred as V19 UNet++. As for the mass localization results, we measure the performance of single-scale detection using the free response receiver operating characteristic curves, which plots the true positive rate against the average false positive per image using various thresholds. And to evaluate the multi-scale fusion strategy, since multi-scale fusion uses an empirical threshold lambda to make final decisions, we tested a set of lambdas to get different scores, which are plotted using stars. We can see that these stars are all located in the upper left corner of FROC space, showing that the mass localization using multi-scale fusion has a higher true positive rate and less false positive proposals compared to single-scale detections. What's more, we can observe that the false positive tend to be reduced at higher lambda, while the true positive rate reaches the peak levels at around lambda equals to 0.506. For mass segmentation, we compare the proposed V19 UNet++ with the baseline UNet, as well as two other recently published architectures, the conditional GAN and the cascaded UNet. This table shows comparative segmentation results on 2048 times 1024 full mammograms for each model in three schemes, respectively one-stage segmentation, two-stage segmentation without multi-scale fusion, and two-stage segmentation with multi-scale fusion. The one-stage segmentation means that to segment directly from the full mammogram using the segmentation model without the localization step. So comparisons between models indicate that the proposed V19 UNet++ yields better segmentation results, with around 28.27% dice improvement compared to one-stage segmentation and around 18.79% improvement compared to segmentation without multi-scale fusion strategy. Here we also present the visualization results on full mammograms. So at the top is the final delineation using two-stage without multi-scale fusion, and at the bottom is the two-stage with multi-scale fusion. It can be seen that the bottom ones have more accurate detections and boundary adherence. False positive proposals are eliminated, and the false negative of the top ones are detected. Moreover, our method is robust in dealing with masses of any size, shapes, or textures. So to conclude, we propose a two-stage framework with a new multi-scale fusion strategy for automatic and precise mass segmentation from native high-resolution mammogram. Through our pipeline, we drastically reduce the number of unsuccessful detections while allowing a variable number of candidate regions to be automatically selected for segmentation without any expert interventions, leading to a more reliable mass delineation from full mammograms. The proposed approach can be easily integrated into clinical routine and is able to help diagnosis by acting as a relevant, fully automated second opinion. Thank you for your attention.